I'm Aaron. I did the Raspberry Pi development for the team.
Hi, I'm Andrew Gillis. I am the mechanical and electrical engineer, and I also worked on the movement development.
Hi, I'm Aiden. I did the display as well as some of the movement, and Ben couldn't join us, but he was part of the audio development. A little bit about our project. As the title may suggest, we are looking to make a chessboard with automated movement and keep it under a certain budget. That certain budget that we defined as affordable was $150, and we were able to achieve that, as well as the automated movement. There are a couple other key values that we were looking for. Capability for online play. Aaron implemented that through the Lichess API on the Raspberry Pi. We wanted to keep everything open source so that after us, if others wanted to download our repository, make their board at home, they could modify it to their liking, anyway, from the code to the board itself, modifying even the game that's being played. And then customizability. So, due to the nature of the pieces being 3D printed, you could change the color of the board, you could change how the pieces are designed, you could change, like I said before, the game that's being played on the board. It's all very customizable. To expand on the affordability a little bit, here's a cost worksheet that we drew up throughout the project. As stated before, our goal budget was $150. Our total build at current is around $96.56, and after all features are implemented for the final prototype, the plan total is $131.36, which is still under our budget of $150. And now I'm going to hand it off to Aaron.
Hey, I'm Aaron. I worked on getting the board ready for online play. And the way we did that was through a Raspberry Pi with a web server. And we connected the web server to lichess.org, which is a open source online chess playing website. And through that connection, which I'll get into detail in this demo video, we were able to make the board available to play games that aren't locally on the board. So in this video, I'm starting a Python code, or running a Python code, and as you can see, this code will be run when somebody on the board decides to start an online game with their friend, and what will return on the display is this ID right here, and the user or the user of the board's friend can either enter this on another board or can paste this ID after the lichess.org link to connect to the game on the board. So what I'll simulate here is just getting on another Lichess account and entering the game this way through the website. And so once I click join the game, this game should start. And so right now I'm connected to the board, and the board automatically makes the first move. And so what will happen is once this game starts, the user on the board will be notified that is their move. And once they make this move, say they do move to e4, the move will be read into the Arduino, and then that move will be serialized and sent to the Pi, which will then be posted to the Lichess API, and then that move will be reflected on the Lichess UI. And then the flow on the other way, so when somebody on the website makes a move, the Raspberry Pi will read that in from the Lichess API, and then send that move, serialize it, send it down to the Arduino, and then it will be reflected with the movement system on the board. And so currently we have the current code for the Raspberry Pi has this flow working where when somebody on the website makes the move will be reflected on the board. However, we still have some work to do on getting the board to the Lichess API and UI, that flow working. However, that's most likely only a few more hours of work, and that will be working. And once we have those, a full game will be able to be played on the Lichess site on the board, through the Arduino and the Raspberry Pi, and through to the Lichess site. Alright, so now I'm going to hand it off to Andrew.
So this is the final capstone prototype. What it's doing right now is it's homing both axes, so this is the calibration step before we go ahead and actually move any of the pieces.
Pawn to c4.
And then at this point, it's going to continue to move pieces.
Pawn to c4. Pawn kills pawn.
And then here is where we test out the graveyard. So a piece was taken, and because that piece was taken, it's going to go ahead and come off the board so it doesn't get in the way of the other pieces.
That's totally barbaric.
That's wizard's chess.
Is it has two steppers, and those two steppers act as the axes for the rack and pinion. So in this case, the mechanical design is a fixed rack, movable pinion, and basically that allows for these axes to be able to move forward and back. So essentially what's happening is there is a servo underneath that is alternating between a north side of a magnet and a south side of a magnet and in between. And that basically allows for us to pick up black pieces which have the south side down or white pieces which have the north side down. The reason we have the black have one side down and the white have the opposite side down is because we wanted to have color identification, and the reason we need color identification is because when there's an option to be able to take two pieces, you need to be able to determine what piece was taken by the opponent. So this all comes back to the detection system. And the detection system is a linear Hall effect sensor underneath every one of the tiles. So essentially the linear Hall effect sensor is detecting magnitude of a magnet. So for example, if there's no magnitude, then we can detect that there's no piece on that tile. But if we detect that there's a positive magnitude, then we can detect it's like a black piece. If it's a negative, then it's a white piece. Since the linear Hall effect sensor can only detect color and presence, we need to know what types of pieces are where. And the way we do that is through a finite state machine. And we have the initial configuration of the chessboard at the very start of the game. Every subsequent move from the computer and the player will be tracked, which allows us to know the board state at all times. Okay, so let's go ahead and talk about the general chess algorithm for movement. So the way we define tiles in the Arduino chess firmware is X and Y coordinates. And instead of using E and A through E and 1 through 8, we use 0 through 7 and 0 through 7. This makes it easier to calculate different diagonals and things for movement code. Since we're getting things from Lichess, it makes more sense to convert that into a number-based system than it is to keep the letter and number-based system. So let's go ahead and talk about some of the different strategies for different types of piece moves. So let's say, for example, the knight wants to move out, and this is a computer move. So in this case, the knight can't get out because of the pawn here, but there's a few options we can do. We can go around the outside of the board and arrive at the destination. So that would be basically you would go through the graveyard and come back around, or there's a push algorithm design that would work as well. So basically this pawn would come out first, and then you would be able to then move the knight over, and then you would then take that pawn and move it back into position. And by doing that, it basically allows for any move to occur pretty easily. And if, for example, you have to move more than one piece, then you could just add that to a stack, and it would then reverse all the moves that you made in order to move that piece. So another common problem with the chessboard in terms of the analysis of the algorithms that people think of is over here with castling. So the problem with castling is it's a double move. So how do you detect that? Because if you lift the king and you move it over and you swap these, you can tell that a castle occurred, but what happens when they want to reverse a castle? So say these are up here. The board won't be able to know if they decide to undo their move. So in the algorithm, we'll just say that if they attempt a castle, if they lift the piece, it's going to be a permanent operation. And then the last type of problem is when two pieces can be taken. This was originally when the system was only presence using a digital Hall effect, and that basically just detects any magnitude. So originally all the pieces had the north side down, and what that meant is that we only had one magnet side up, and that was the south side. So basically, let's go ahead and take a look at that example. So say this piece was out here, and then say this piece over here moved up. Now, I can take the piece over here and the piece over here, but the problem with that is then the detection system. So the detection system can't tell if it's only presence, did I take this piece over here or did I take this piece over here? It just can detect that this piece is no longer here. So that is an issue. The way that that's fixed is with the linear Hall effect. If we can detect presence, then when this piece is up here and this piece is over here, if it takes this piece, then we know, okay, there's a new white piece over here where it used to be a black piece. So then we know this piece was taken. So that's how the logic of that breaks down. And then finally, let's talk about scanning methods. So there's a few scanning methods that we went over in terms of the design. So the first one is an O of 1 scanning method. So that means every tile has a linear Hall effect underneath it. And that basically means we can instantly scan all the tiles all at the same time. That basically means if you lift a piece, then we know exactly that a piece was lifted. Of course, these are running through multiplexers, so it's not 100% instant, but it's pretty close to being instant. The next method is a O of n algorithm, n squared algorithm. And essentially what it's doing is it's scanning line by line for changes. So it just goes like this, and it continues scanning until it notices a change. And because it, as soon as it notices one change, then we can stop because we can assume that a person isn't going to make two moves. The only problem with doing a scan like this is the you're going to have to be constantly moving on the scan. It does limit the number of Hall effects you need because you only need one to do this method versus 64 if you were to do the other method. So it makes it a lot easier in terms of hardware implementation, but it does slow down the scanning method. And then the third method is a intelligent scanning method. So instead of doing this curve and scanning and continuing to repeat that every time, you should only scan the ones that are even possible. So, for example, it's white's turn, right? So white's going to move. You don't really need to check the moves that are impossible. So let's look at all moves possible. So this move's possible, this move's possible, and then every move like this is possible. Okay. So let's go ahead and see what the minimum number of scans are for detecting this. So the first one you should probably scan is the pawns. And the reason why is if a pawn's missing, then you know a pawn was taken. And then the next one you should scan is the one up here. And subsequently, or I mean instead, you can actually scan here. And the reason why is it's basically a logical proof. So if we have a pawn, for example, this pawn right here, let's go ahead and show that. We have this pawn move up to here. When we go to do that first initial scan here, we say, oh, there's a pawn missing here. And then when we go to do this scan, we notice the pawn, there's a new pawn up here. And then because this pawn was missing, we know, oh, this pawn must have moved up. Now, the question would be, how do we know if a knight moved up? So say we scan. So say we scan here, and then we scan here, right? Then we notice there's a piece here. Well, we scan here and all the pawns are here, so that means it must have been this knight, because this knight can't be all the way over here. And no other piece can jump besides the pawns can go up, and of course the knights can jump. So let's go ahead and take a look at the final part of this proof. So the reason why we only have to scan these two and not this third one is because if it's not here and it's not here, it has to be here. And that's just because of the way that the pawns can move. So for an opening move checking, you don't need to scan that often. And then for subsequent scans, you can find the minimum span of the possible moves and their scanning positions. So for example, say this piece was up and then this piece was out. Then basically you would look at all the possible moves of each piece and then find the lines that would entail these sections. And that would be the smart algorithm. Of course, worst case is still O of 1 squared, except it's significantly faster, and of course the average will be faster as well. Thank you for watching our automated chessboard video. A lot of fun was had on the way in designing and implementing this chessboard. If you wish to learn additional information about the CAD, the electrical engineering, or the software, please go to the GitHub page for Affordable Chessboard. Thanks!